Good morning, class. This is Mr. Eggleston, and this is lesson 8.3, graphs of the parent exponential functions. This is for Algebra 1. The learning targets we have for this lesson is graph equations of the form y equals b to the x. We're going to learn what the graph of them look like, and identify and this is kind of important, you will identify the domain, the range, and the y-intercepts, and this new word, asymptotes. And we'll define that in this lesson, what an asymptote is. We'll explain why all functions of the form y equals b to the power of x, b to the x, pass through the point 0, 1, which is easy to understand, and 1b. Both of these are real, just like in your face, easy to understand, because remember, if x is 0, then y would equal b to the 0 power. And any number to the 0 power, except for 0 to the 0, that's a special case, but any number to the 0 power is always equal to 1. So that's always true. So it doesn't matter what the base is. If it's y equals b to the x, then 0, when the y-intercept, this is the y-intercept, will be at 1. It will pass through 1. And when x equals 1, same idea. Now it'd be y equals b to the first power, which is just b by definition. Okay? Those are easy to explain. Okay. Understand that if b is greater than 1, this is key too. If b is larger than 1, the function is increasing. The slope of the graph is positive. That's tied to the fact that the function's increasing. And the function represents exponential growth. Okay? And if b is less than 1 but greater than 0, b is positive. All right? So if b is less than 1, the function's decreasing. So b less than 1, the function is decreasing. Slope of the graph is negative. That's tied to the fact that the function's decreasing. And the function represents exponential decay. Okay, and we're going to get into that, and we're going to get into what the graphs of those look like. Okay, they all have the same overall shape. Before we get into this, an important concept for you guys to know is, remember your basic properties of exponents. If you have, let me just go through this. If you have 3 to the third, you know that's 27. If you have 3 squared, you know that's going to be 27 divided by 3 is 9. 1 to the first is just 3. Got to scoot down and give myself a little more space. All right. If we keep going, notice that each time we decrease the power, we are dividing by 3. So that tells us 3 to the 0 is going to be 1. Why? Because that is 3 divided by 3. And guess what 3 to the negative 1 is? We take 1 and divide it by 3, and it is 1 over 3. And the next one, 3 to the negative 2, would be 1 over 3 squared. So you have to remember that negative exponents moves the base downstairs. Okay? That's an important concept, because you get, it's 3 to the negative 2 is not negative 9. It's 1 over 3 squared, which is 1/9, which is smaller than 1/3, which is 3 to the first, which is smaller than, 1/3, which is 3 to the negative 1. And 1/3 is smaller than 1, which is 3 to the 0. So I'm just looking at these, right? And then it goes 3 to the first is 3, 3 squared is 9. So you have to remember that when the exponent's negative, the base moves downstairs, and now instead of being like in this case, 3, it'll be 1/3 if it was 3 to the negative 1. All right, that's an important concept. So here we go. We spent the past 2 days thinking about scenarios, situations that represent exponential growth. Today, we're going to look at exponential functions from a graph perspective. So they want you to fill out the table. So I always tell students start at 0 because that's the easiest. We know that. We know 2 to the 0. Let me shrink this because it's a little fat. Something my wife has never said I was. She just says I'm fat. So 2 to the 0 is 1. 2 to the first is 2. 2 squared is 4. Notice they give you a decimal here. I can't do that in my head. I'd have to have a calculator, and I'll get back to it. And then 2 to the third is 8. We're multiplying by 2 going up. And then 2 to the fourth is 16. Now, to show you how to calculate 2 to the 2.5, they're trying to show you that x can be any number, any rational number. Actually, it can also be irrational, but I don't think we get into that in this class. All right, but if we wanted to do this on our calculadora, you literally, sorry, it takes a sec. Clear. 2 to the power of 2.5. That's that's an ugly decimal. It's 5.6568544249. And that's to however many decimals is showing. What is that, about 8? 1, 2, 3, 4, 5, 6, 7, 8. 9 to 9 decimals. So we would say it's about, let's see if they tell us to round to the nearest tenth or something. They don't really say, so I'll just go to the nearest hundredth. So this is 2, I'm sorry, it's not 2. It is 5.66. Okay. So this is 5.66. All right. And then now let's go in the negative direction. So this is 2 to the negative 1, which is 1 over 2 to the first, which is 1/2. This is 2 to the negative 2, which is 1 over 2 squared. Notice once you move the base, once you move it, in other words, once this drops downstairs, leaves a 1 on top because there's a 1 multiplying the 2 to the negative 2. It's 1 over 2 squared, and that is 1/4. Okay, so let's plot these points. Oh, they're right here. So notice we have 0, 1 is already plotted, is right there. 1, 2, 2, 4, 3, 8, 4, 16. So, and they wanted us to highlight the y-intercept, which is both on the graph, which it already is, it's right there, and then in the table. The y-intercept is always when x is 0, okay? So let's go ahead and plot the other two numbers. When x is negative 1, we're at 1/2. So that would be roughly right there, halfway between 0 and 1. And then we got 1/4, which is at negative 2, which is even closer. Okay, so we have a graph doing something like this. Okay. Notice it is smooth. And it apparently keeps going up. the further to the right we get to. And it keeps flattening out the further to the left. What happens to the y values as x gets larger? Y gets larger. Okay. What do you predict will happen to the y values as x gets smaller and smaller, more negative? Well, it looks like as x gets small, y goes to 0. Y gets smaller. So this is, we call this, that approaches y equals 0 asymptotically, okay? So let's just test our conjecture. Let's go ahead and calculate 2 to the negative 100 power. And you're going to see your calculator kind of hiccup here. It's not going to like it too much. Oh, no, not open, not open. Shoot, there we go. So it's 2 to the power of negative 100. And notice it gives you a weird answer. 7.9, I'm just going to one decimal. And then this notation at the back end is called scientific. So this equals 7.9 times 10 to the, and we didn't get into it too much, 10 to the negative 31. Your science courses will. What this means is that exponent tells you how many times we move this decimal point. Since it's negative, we move in the negative direction. So we have to move this decimal point to the left 31 times, which means this equals 0. Now that you will have 30 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then it will be 7, 9. Look how many zeros. I mean, I had to write them small and messy just to get them to fit. And these last few in the back here don't even look like zeros, but they are zeros. That's how many zeros. That's how small that number is. But notice that number is not negative. That number is just really close to 0. Okay? So, what do you notice? The number is practically 0. I mean, okay? And we call that the asymptote because the graph will keep getting closer to that 0 number but never touch it. So we would say that y equals 0 is an asymptote. It's the line the graph approaches as x, and this is as x goes negative. As x goes to, and we usually use negative infinity to represent going on forever to the left, all right? So the horizontal asymptote is the value that the graph, is the line that the graph approaches but actually doesn't touch, okay? So for which values of x will y equal 2 to the x be equal to 0? For which values of x will y equals 2 to the x have negative outputs? No x values, right? Because you see negative 100, I could have gone negative 200 and it would still be, it will not be 0. It'll be practically 0. It will be so small that you would treat it as 0, but it's not really 0. And because it never gets to 0, it will never cross the x-axis. So no x values make 2 to the x equal to 0, and likewise, no x values can make 2 to the x equal a negative number. Okay? Can't do it. So we say y equals 0 is the asymptote. It's the line that the graph approaches but doesn't touch. Okay? Says, now that was exponential growth. Couple things. Do you notice that it blows up real quickly going to the right? It'll keep getting higher and higher. And it flattens out going to the left. And it flattens out at y equals 0. Okay? So what happens to the y values as x gets larger? Okay. It gives you the y-intercept of 0, 1, and also, right here. What happens? So 0, 1 is the y-intercept. Okay. What happens when the y value gets larger? What do you predict? So we say the horizontal asymptote is at y equals 0, because as we move off to the left, that means negative. The numbers approach y equal to 0, but it doesn't actually get there. Okay? It's like the x-axis is a giant wall. Okay, so if this is the x-axis, and the graph is coming in, and it sees this wall, and it's got to turn because it doesn't want to crash, so it's going to turn to follow it. All right, it can turn that way, or it could turn this way. It will turn to follow the y-axis. All right? And we call that line that the graph approaches but doesn't touch the asymptote. And in this case, it's the x-axis. So I should say as x gets small, I should say as x gets negative, or very negative, y goes to 0. All right. For which values of x will 2 to the x be equal to 0? And this tells us that the range is, remember the range is the output, is y is greater than 0. It will never go past 0. So the graph will always be above the x-axis. And that's the range. Okay. Now, and notice the base was 2 on this. And the graph, as you watch it, this graph, as we go out, blows up, gets bigger and bigger. We call this exponential growth. Okay, so this is, oh, come on. Sorry, children. This is x. I'm going to lower it, so exponential growth. R, which is the base, is equal to 2, which means R is greater than 1. Okay, because 2 is greater than 1, and that's exponential growth. All right? Now, we're going to do a similar thing for question 6. Except for now, do you notice the base is 1/2? So, let's do it blue. Let's start with 0. We have 1/2 to the 0 power is 1. Okay, because any number to the 0 power is 1. 1/2 to the first power is 1/2. 1/2 to the second power is 1/2 times 1/2 is 1/4. And then lastly, on the positive side, 1/2 to the third power is 1/8. Now, if we go in the negative direction, you get 1/2 to the -1. Remember, the base wants to move. So the 2 goes upstairs and the 1 goes downstairs. That's the same thing as saying 2 to the first, which is 2. We had the negative exponent means we have to take the base and take its reciprocal. Then we have 1/2 to the -2. Remember, negative exponent flips the base, so now it's 2 over 1, which is 2, squared, which is 4. And lastly, we have 1/2 to the -3, which is 2 over 1 to the third, which is 8. So now, as we go out here to the negatives, we're at 8. And then we're at 4. And then we're at 2. Okay. And then we're at 1. And then we're at 1, we're at 1/2. We're at 2, we're at 1/4. So we're getting closer. And you can just imagine that this graph is going down to the x-axis. And you can see that if we're at -4, they don't have it here, but if we had a -4, that would be 1/2 to the -4, which is 2 to the 4th, which is 16. So at -4, we're at 16. And our graph looks something like this. All right, and it keeps going up. All right. Notice, this is exponential decay. The base was equal to, what was it? It was 1/2. So, which is r, and r is less than 1. So as we go out to the right, the graph approaches y equals 0. It looked very much like the exponential growth graph, except for we call it a reflection across the y-axis. If you compare the two graphs, they are the same, only the growth graph blows up to the right. They both pass through 0, 1. And the decay graph goes down to the right, again passing through 0, 1. Okay? So they ask you what is the same? They both have the same y-intercept. That is 0, 1. What is different? Y equals 2 to the x is exponential growth. And y equals 1/2 to the x. Notice I put parentheses around the 1/2. Okay? Is exponential decay. Because it gets smaller to the right. And to the right is as x gets bigger. Okay? So, write these little blurbs down. The range is still y is greater than 0. Because the output is only above. The lowest it gets is close to 0. And then it's always above. So the range is y is greater than 0. The y-intercept is 0, 1. And that's because 1/2 to the 0 is 1. And also something that's not written here is that the domain, all the input, the domain is all real numbers. X can be any number. And if you plug it into your calculator, where x is any number, it will spit out a numerical value. So the domain is all real numbers. There's no exclusion, no points that make the domain go bad, the function go bad. All right? So, putting it all together, here's your quick notes. Quick notes. The most basic exponential functions have the form y equals b to the x. They call this the parent exponential function, where b is some positive or some non-negative number. All right? The domain is all real numbers. The range will always be y is greater than 0. The y-intercept is 0, 1, and they tell you because b to the 0 power is equal to 1. Growth decay factor, b, the base tells you if it's growth or decay, because if b is greater than 1, it's growth, and if b is less than 1, but greater than 0, it's going to decay because we're multiplying by a number smaller than 1 each time, which shrinks your output. All right, they both have horizontal asymptotes, an asymptotic line that affect y equals 0. And you usually put a dashed line at that location. This dashed line represents the horizontal asymptote. Okay? And there you go. Again, two different shapes. They are, if in geometry you're going to learn about reflections, they are reflections across the y-axis. That is, each of these graphs, this one blows up to the right, this one decays, goes to 0 to the right, and every point that's on this graph here is on the other graph, just reflected at the same distance from, at the same x values. So, in other words, for growth, it would be b to the negative, or b to the 3, and let's say b is 2, so it'll be 2 to the third is 8. The decay would be b, 8 would be at b to the negative 3, because decay would be 1/2. Anyway, and also the bigger b is, the more steep the graph gets. In other words, it blows up faster. And there you go. Have a good day.